Welcome to the class. In our earlier video with the title The Synthesis of Oximes from Aldehydes and Ketones, we have learned as to how to convert a cyclic ketone into a cyclic oxime. In this video, we conceptualize the conversion of a cyclic oxime to a cyclic amide. A cyclic oxime to a cyclic amide, which is also called as lactam. This is an amide and this is amide in a cycle. Therefore, it's a cyclic amide or a lactam. And to make the lactam from cyclic oxime, all you have to do is to treat this cyclic oxime with a mineral acid. The reaction is referred to as the Beckmann rearrangement reaction. The Beckmann rearrangement reaction involves the dissociation of H plus from a mineral acid. The dissociated H plus now attacks the lone pair of electron on oxygen atom. When it attacks, the oxygen atom becomes positive. This is because it consumes the lone pair of electron. The positively charged oxygen atom now tries to withdraw the shared pair of electron towards itself. When it does, the oxygen's neutrality is restored and there is elimination of water. As for nitrogen, because it's lost its one electron to the H2O plus molecule, the nitrogen becomes positive. A positively charged nitrogen atom is very electronegative. It exerts a pressure on electron pair at adjacent positions. So either it can try to extract this electron pair or it can try to extract this electron pair. Both are same because the compound is in a cyclic form. Now assume that it tries to extract this electron pair. Then in that case, this carbon atom, this crossed carbon atom here, it would form a bond with the nitrogen atom. And this carbon atom, it just lost one electron to nitrogen. So therefore, this carbon atom here, it would become positively charged. So now this carbon atom, this crossed one, it is linked to nitrogen atom. The positively charged carbon atom, it is also linked to nitrogen atom by double bonds. However, these two, the crossed atom and the positively charged carbon atom, are not linked to each other now. They are linked to nitrogen. That means nitrogen takes the middle position in between the crossed and the positively charged carbon atom. Also, now it is not a 6-membered, rather it is a 7-membered ring that includes nitrogen. This is represented by this structure. As you can see, the nitrogen takes the center spot. This is the crossed atom which forms a bond with nitrogen, and this is the positively charged carbon atom which bonds with nitrogen through double bond. Now this positively charged carbon atom, it attracts the electron pair on the oxygen atom of the water molecule that was eliminated in the step preceding to this. When this water molecule gets attracted, the oxygen, it gives the lone pair of electron to this carbon atom, and this carbon atom's neutrality is restored. And because oxygen has given its lone pair, the oxygen becomes positive in charge. To restore neutrality, oxygen tries to withdraw electron from one of the hydrogen atoms. Suppose it withdraws from this hydrogen atom, then oxygen's neutrality gets restored, and so it becomes OH here, and a molecule of H plus is eliminated out. That is, acid is retained in the system. Now this is the enol form. Recalling that enol is the functional group in which OH is attached to carbon, which is attached to nitrogen by double bond. So this functional group is called as the enol. The enol form tautomerizes to the keto form at room temperature. The keto form is in majority. It is seen that the keto form is 76% and the enol is 24%. When the keto form is formed, we get our product which is lactam or cyclic amide. So if you can see here, there are three key movements in this reaction. The first is the reduction by H plus by the acid. The first is the reduction by the acid. The second is the rearrangement of the electron pairs. And the third is the retainment of the acid in the system. So therefore, the Beckmann rearrangement is acid catalyzed reduction and rearrangement of cyclic oxime into a cyclic amide. To understand this reaction better, let us look at the mechanism. Let us now look at the mechanism of Beckmann rearrangement. This is our raw material, the reactant cyclic oxime, and this is our product lactam. If you look at our product, the nitrogen here is substituted with hydrogen, while here the nitrogen is substituted with OH. So our first objective is to remove OH, but it is not so easy as it seems to remove OH. This is because oxygen has got two lone pair of electrons, and that makes the oxygen excessively electron rich. And because oxygen is excessively electron rich, it is heavily attracted to the nucleus of the nitrogen. It is a very good base because it has electrons to be donated, and it is a very poor leaving group. So our first strategy is to somehow reduce the electron density on the oxygen atom. It is for this purpose that we use an acid. When we use an acid, H plus gets dissociated from acid. The dissociated H plus now goes and attacks one of the lone pair of electron on the oxygen atom. That results in a positive sign over the oxygen atom. Now there is scarcity of electron on oxygen atom, because of which it is not as much attracted to the nucleus of nitrogen as it was before when it was neutral. Also, the electronegativity of oxygen has increased manifold because of the scarcity of the electron. Because of these two factors, the electron pair that is shared between the nitrogen and oxygen now drifts towards the H2O plus molecule, leading to the elimination of water. Now because nitrogen has lost its one electron from among the shared pair of electron to H2O plus, nitrogen now becomes positive. The electronegativity of nitrogen has increased manifold because of the positive sign over it, and the positively charged nitrogen atom now tends to exert pressure on the electron pairs at adjacent positions. So there are two adjacent positions here, the 2n7 position and the 2n3 position. Assume that it is successfully able to extract electron from 2n7 position. If so is the case, then the 7th carbon atom, it will be attached to nitrogen in this manner, and because second carbon atom has lost its one electron to the nitrogen atom, while formation of bond, the second carbon atom becomes positive. However, second carbon atom is still attached to nitrogen atom by double bond. Here is the double bond. There is no connection now between the 7th carbon atom and the second carbon atom, right? Because the 7th carbon atom is connected to nitrogen, second carbon atom lost its electron to nitrogen, the second carbon atom is directly connected to nitrogen by double bond. So there is no connection between 7th and second carbon atom. Nitrogen comes in between, right? This is the way the 7th is connected to nitrogen, the nitrogen is connected to second by double bond, and because the second has lost one electron, it is positively charged. Now this acts as a very strong Lewis acid. It attracts the Lewis base here, Water that was released in the step preceding to it is amphiprotic in nature. It acts as Lewis base when it encounters a Lewis acid. Here it encounters a Lewis acid, and when it encounters a Lewis acid, what it would do? It would act as a base, donating the lone pair of electron that was on the oxygen. And when it is donated, when the lone pair of electron is donated, the carbon's neutrality here is restored. However, oxygen becomes positive because it's just donated its lone pair of electron. Now to restore neutrality, oxygen, it extracts the electron pair towards itself. So the H plus now gets dissociated from this system. The H plus gets dissociated, therefore the acid is acting as a catalyst here because it is getting retained in the system. Oxygen, however, successfully restores its neutrality. Now the hydrogen, it migrates to nitrogen. This is the enol form that is formed. Recalling that enol is a functional group where the OH is attached to carbon, which is attached to nitrogen via double bond. This is the enol form. Intramolecular arrangement takes place in the enol form. The H here migrates to nitrogen. When it migrates, the H consumes the lone pair on the nitrogen, making it positive. When it migrated, it left its electron pair here. The nitrogen here, to restore neutrality, pulls this electron pair towards itself, and when that happens, the carbon atom here becomes positive. The positively charged carbon atom now pulls the electron pair from here, and that results in the keto form, which is a lactam or a cyclic amide. The enol form and the keto form both are tautomers. That means they coexist with each other at room temperature. However, keto form is in major proportion. 76% of it is keto form and 24% is enol form. The reason why keto form is formed in dominance is because the keto form is thermodynamically more stable. More energy is released in the formation of carbon double bond O rather in the formation of the carbon OH bond. That makes it a more stable molecule. Therefore, the keto form is formed in major proportion. Therefore, the formation of lactam occurs. There are three key movements here in the reaction. One is the reduction. The second is the rearrangement within the ring. And the third is the retainment of catalyst. So the Beckmann rearrangement is acid catalyzed reduction and rearrangement of a cyclic oxime to a lactam.